Welcome to today's paper reading. Today's paper is titled, Camera Calibration Using a Collimator System. This paper was published on AR14 by Shunkun Liang and colleagues from the College of Aerospace Science and Engineering at the National University of Defense Technology. The abstract highlights the importance of camera calibration in photogrammetry and 3D vision applications. It points out the difficulties faced in practical scenarios with long working distances and site limitations. To address these challenges, the paper introduces a novel method using a collimator system, which provides a reliable and controllable environment for calibration across varying distances. The method simplifies the relative motion between the target and camera to a 3DOF pure rotation motion, and proposes both a closed-form solver for multiple views and a minimal solver for 2 views. The effectiveness of this method is demonstrated through both synthetic and real-world experiments, showing its superiority over existing state-of-the-art methods. Geometric camera calibration is crucial for mapping 3D rays in space to 2D image pixels. This process is fundamental for various vision applications like SLAM, SFM, and pose estimation. Traditional methods using planar targets are prevalent in 3D vision but face challenges in long-range scenarios, requiring large targets and dealing with unstable lighting conditions. In this paper, a novel collimator system is proposed, featuring a structured calibration pattern. This system reduces the number of motion parameters to be estimated and eliminates the need for direction measurement, making the calibration process more flexible and accurate. Figure 1 illustrates the collimator-based calibration method. The inherent optical geometric properties of the collimator system allow for the relative motion between the calibration target and the camera to be proven as conforming to the spherical motion model. This constraint effectively reduces the original 6 degrees of freedom, DOF, of general motion to 3 DOF of pure rotation motion. The figure also highlights the development of a closed-form solver for multiple views and a minimal solver for 2 views, which are essential components of the proposed camera calibration method. Camera calibration in 3D vision is a critical area of research. Target-based calibration methods use various types of targets such as 3D, 2D, and 1D targets to ensure high accuracy. Self-calibration techniques, on the other hand, establish image correspondence during camera movement without the need for a calibration target. Collimator-based calibration provides a precise and flexible solution within limited spaces, though it often requires expensive equipment like goniometers or theodolites. The collimator system designed in this paper features a star-based pattern attached to the reticle, which provides rich gradient information for accurate feature extraction. This system is portable, measuring approximately 200 mm by 170 mm by 300 mm, making it suitable for special calibration scenarios such as limited space and long-range cameras. The system's operation is based on the spherical motion model, where the relative motion between the calibration target and the camera conforms to a pure rotational motion. This is due to the angle invariance property, which ensures that the angular distance between any point pairs on the target remains constant regardless of the camera's pose. The calibration method reduces the general 6 degrees of freedom, DOF, motion to a 3 DOF pure rotational motion, with a fixed translation vector that does not depend on the target's pose. The mathematical representation of the relative pose between the camera and the calibration target is given by a transformation matrix, which simplifies the calibration process. Figure 2 illustrates the diagram of the collimator system, highlighting its geometric properties. The collimator system is designed to maintain the angle invariance of any point pair on the reticle. This property is crucial for the calibration process, as it ensures that the relative motion between the calibration target and the camera conforms to a spherical motion model. The figure shows the essential components of the collimator, including the light source, reticle, and optical lens. The reticle, a thin glass located on the focal plane of the collimator, plays a key role in generating collimated rays. These rays can be considered as the inverse process of imaging a target at infinity onto the focal plane. The figure also visualizes the propagation routes of the 2 beams generated from points P1 and P2 on the reticle, which are observed by cameras C1 and C2 with arbitrary poses. The angle between these two lines observed by the cameras remains constant, demonstrating the angle invariance property. The camera calibration method presented in this paper involves several key steps. First, the authors used a pinhole camera model to establish geometric constraints. This model includes the intrinsic matrix K, which consists of focal lengths, principal points, and a skew factor. The transformation between the image plane and the calibration target plane is governed by a homography matrix H. For multiple views, a closed-form solver is proposed, which models the problem as a linear system. This involves calculating the determinant of matrix M and selecting a base image. In the case of only two views, a minimal solver is introduced, which constructs a nonlinear equation system using the hidden variable technique and solves it via Cholesky factorization. In this section, we present the evaluation and results of our proposed algorithm. First, we discuss the synthetic data experiments, where we evaluate the robustness and accuracy of our algorithm against noise and compare it with other methods like Zhang, Baguette, and Hartley. We also examine the sensitivity to imperfect spherical motion. Next, we move to real images experiments, where we assess the calibration and accuracy by comparing reprojection errors and evaluating the epipolar rectification error. Finally, we explore the calibration of multiple cameras with different focal lengths using the same collimator system, demonstrating the lowest reprojection error and confirming the effectiveness of our method. Figure 3 illustrates the comparison of calibration errors with increasing noise levels. The calibration error increases linearly as the noise level rises. The proposed algorithm demonstrates greater robustness to noise compared to other algorithms. Notably, at a noise level of 0.5 pixels, the proposed algorithm outperforms the other three algorithms, indicating its superior performance in handling noise. Figure 4 illustrates the comparison of calibration errors as the number of images used for calibration increases. The study evaluates the performance with respect to the number of calibration images, ranging from 3 to 30, with 200 trials conducted for each quantity. A significant decrease in error is observed when increasing the number of images from 3 to 5. This figure highlights the effectiveness of increasing the number of images and reducing calibration errors, which is crucial for achieving more robust and accurate calibration results. Figure 5 presents the sensitivity analysis of initial value estimation with respect to imperfect spherical motion. The experiment evaluates the impact of adding zero-mean Gaussian noise with standard deviations ranging from 0 mm to 30 mm to TCP, simulating imperfect spherical motion. Using 15 images and adding a noise level of 0.5 pixels to the image points, a total of 500 independent trials are conducted for each noise level, and the average errors are computed. The results show that noise has no impact on Baguette and Zhang, as they do not rely on the spherical motion constraint. As the noise increases, the calibration errors of ours and Hartley increase gradually. Notably, Hartley is significantly influenced by noise, whereas ours displays superior robustness. Even with noise levels below 15 mm, equivalent to 2.143% of the spherical radius, our algorithm remains superior to the alternatives. Figure 6 presents a sample of calibration images obtained from a collimator, which are used for evaluating the performance of our method on multiple cameras with varying focal lengths. The cameras used in this experiment include those with 12 mm, 16 mm, 25 mm, and 35 mm lenses. These calibration images are crucial for ensuring the accuracy of the camera parameters, as they are captured from the same collimator, providing a consistent reference for calibration across different camera setups. The figure visually demonstrates the type of images used in the calibration process, highlighting the importance of the collimator in maintaining accuracy and consistency in multi-camera calibration. Table 1 presents a comparison of calibration and pose estimation error results in pixels for 4 different methods: Baguette, Hartley, Shang, and ours. The table details the reprojection errors denoted as calib and evil for each method across various numbers of images used for calibration. Despite having a slightly higher calibrated reprojection error, calib, our method, ours, exhibits the lowest reprojection error in evaluation images, EVEL, compared to the other methods, indicating that our method achieves more precise camera parameters. This comparison highlights the effectiveness of our approach in minimizing evaluation errors, which is crucial for accurate camera calibration. Table 2 presents a comparison of calibration results using 20 images captured by a real camera. The table includes parameters such as fx, fy, cx, psi k1, and k2, which are crucial for camera calibration. Additionally, it provides the calibration error, calib, and evaluation error, EVEL, for each method. The comparison is made against the Baguette, Shang, and Hartley methods, highlighting the performance of our proposed method in terms of lower evaluation errors, indicating more precise camera parameters. This table is essential for understanding the effectiveness of our calibration method in real-world scenarios. Table 3 presents a comparison of epipolar rectification error results in pixels. The table shows the mean and standard deviation of errors for different methods as the number of calibration images increases. It highlights that as more calibration images are used, the error stabilizes, indicating improved accuracy. The use of Collimator images further enhances this accuracy, demonstrating the beneficial impact of the spherical constraint. Additionally, the results show that our method achieves comparable evaluation errors without relying on assumptions like gamma equals 0, as commonly used by Zhang and Baguette. Table 4 presents a comparison of calibration results obtained using different focal length lenses, measured in pixels. The data indicates that the reprojection error tends to increase as the focal length of the lens increases. Among the evaluation images, the proposed algorithm demonstrates the lowest reprojection error for lenses with varying focal lengths. This trend suggests that shorter focal lengths generally result in lower calibration errors. The results confirm the effectiveness of the proposed Collimator system and method, highlighting its superiority in camera calibration accuracy compared to existing methods. This paper introduces a new camera calibration technique utilizing a specially designed Collimator system. The method is based on the optical geometry of the collimator, demonstrating that the relative motion between the target and the camera follows a spherical motion. Additionally, the paper presents a closed-form solver for multiple views and a minimal solver for 2 views, enhancing the calibration process. The collimator-based approach effectively merges the benefits of close-range calibration with a collimator and the flexibility of a planar calibration target. Experimental results from both synthetic and real data confirm that the proposed method outperforms current state-of-the-art techniques in calibration accuracy. However, the paper acknowledges a limitation in calibrating fisheye cameras, where more attention to distortion is necessary. Future research will concentrate on improving calibration methods for cameras with significant distortion. This research was made possible through the generous support of the Hunan Provincial Natural Science Foundation for Excellent Young Scholars, under grant number 2023 JJ20045, and the National Natural Science Foundation of China, under grant number 123721189. Additionally, we would like to acknowledge Zijia Wang for their valuable discussions that contributed to the writing and refinement of this paper. Thank you for watching.